Yo, yo, yo. What's up, everybody? Welcome back. Today we are working on our B tree implementation in Zig. Context here. I wanted to make an R tree, which is like some sort of like spatial data structure. Oopsies, I don't know what the fuck I just did that. R tree. Spatial data structure, which would help us maybe with the idea of making sure that we don't do like n squared algorithms when working with spatial data, right? If we're saying like iterate over all nodes close to us right now with no spatial information, we're just kind of saying iterate over all nodes and then check if this node is close to us, which is slow as shit, which makes our code map slow as shit, right? So I wanted to work on R tree, and then I was like, well, I haven't like written a tree structure like maybe ever, maybe in like 10 years. I can't really remember the difference. And I was like, well, I think that it would be a good warm up to write something like a B tree because I think B trees are kind of neat. They're kind of like in the Rust standard library as this like kind of like cool data structure where you're kind of trading you're trying to take the best of both worlds of like a array and like a tree structure, right? Where tree structures allow you to like insert things pretty quickly. They allow you to like reorder elements without like having to touch every element in the tree. But they're slow for iterating because like the memory management unit can't like guess your access patterns as well, right? So B trees, they say, well, what if our nodes just had like 10 elements in them? Then you could, at least as you're iterating over chunks of elements, your memory management unit goes like, oh, yeah, this stuff, I'll bring all this into the cache. And then you like hit the cache and you're like, oh, it's in the cache. Hell yeah, baby. So that's kind of like the idea as far as I care. I don't know if that's like the idea of anybody who wrote it or anything. It's just the idea that I think makes sense. And so we've been working on this thing. We have something that kind of works for like the first layer. So this is an example B tree that we've been making. And so the way that this visualizer is oriented is that we have like the first node here and all of its children directly under it, just similar to like a file system tree view, right? And the way that you like interpret this data is that the first node in the root is 23. So everything in the first node should be smaller than 23, and everything in the other nodes should be greater than 23. And so the iteration order here is you go 2, 6, 13, 19. You finish this, you go to the split point here, 23. Then you come down here, 26, 27, 28, 34, 35, 68, 72, 75, 76, 81, 86, 91, 92. So there's like sorted data in here. Pretty cool, pretty cool. We have not finished though. We've not finished. So the way that like insert this works right now is we get like elements, right? 92. Here he comes in. He's like, oh, there's a slot here. I'm gonna go in there. Bam. 23. Bam. Then he goes, oh, 68. Let me try to put it in here. Uh-oh, there's not enough space. So what he does is he splits this shit in half and he says, whichever thing was in the middle, I'll put that in the root now. Boom. So then we can kind of start filling up these nodes. We go 27. Uh-oh, 27's trying to go in here. There's not enough room. So he slams the 27 in there. He splits out the stuff that was in there before, the 34, 35, and then the 28 pops out because it was the thing in the middle of those 5 elements, and he gets put into the root. Boom. Now you still have like sort of data, 23, 27, 28, 34, 35, 68. Boom. So we can kind of like handle that, okay? Where we start to run into problems is we have not correctly implemented what happens when we try to we try to insert into a full element in the second level. Here, the whole world just like falls the fuck over. What the fuck? So we have to fix this. So that's kind of the plan for today. Try to fix this. Then we should probably implement like a proper in order tree walk. So we should be able to iterate in the order like 2, 6, 13, 19, 23, 26, 27, 28, 34, 35, 68, whatever, right? We should be able to do that, which we can't right now. And then probably we need some way to do like node lookup, deletion. And if we happen to get through all of that, which seems unlikely, then we can start doing like benchmarking and comparison with like, a typical red black tree or something and see how much faster it is. But we won't get there. So it's not worth talking about. So let's get moving. So I think what we want to do is we want to start with this test case. So it would be kind of nice if we kind of just pre-jacked this stuff to the point where it's broken. So it's kind of here. We try to insert 92. So how many elements are in here right now? 1, 2, 3, 4, 8, 12, 14, 18. There's 18 elements in here. So let's kind of like just pre-jack our thing so that when we reset, we go directly there. So probably insert. We probably want to go every time we reset. We go for 0 to B for zero to start test start. I guess we'd call it. For 0 to test start, we get our inserter. Our API to the B tree is kind of like fucked up right now. We should probably fix that actually. So we kind of made this like inserter. The idea here was so that we could visualize like half steps in an insert, right? Which is what we were seeing a second ago, right? Like this fact that the 92 is up here and he's highlighting this thing. This is like the first step of many in one insert. So we kind of made this like state machine so that we could kind of like poke and prod the internals of the insert while we're doing it. But in reality, when you're doing like normal usage of this thing, you probably just want to slam a value in here, right? So we probably just want to go. We probably want to get our inserter, right? And we just literally just run this shit to completion. So while inserter step, yeah. And then looks like we're chilling. It looks like the function name here is colliding, which kind of blows. So I guess we just call this like val inserter just to kind of dodge that. Hell yeah. And so now we should be able to go B tree insert the value in our insert sequence at I. And then we just say insert index is test start, boom, bang, bang, boom, which means that here we probably need to do the same thing where we go like test start. And then we go for 0 to test start I. We do it again here on initialization. Boom, 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 B tree, insert, insert sequence I. Boom. Okay. And this probably has to be tried. All right. Fuck. It never works. It never works. Fuck, 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 fuck. Okay, so what's he pissed about here? Oh. Oops. That guy still wanted to use the actual function, not our bullshit. Okay. Hell yeah. So now we refresh, we step, we reset, we go back to just before stuff falls over, which is big for us. And now we can try to figure out what's wrong. So the first thing I notice here that seems wrong is we get 92 in here. 92's already in the fucking thing. And so the fact that he tries to insert here and doubles up the 92, that's a bug. That shouldn't be happening. And we're supposed to protect against that. We're supposed to. Because here we're supposed to check if the thing exists, and if the thing doesn't exist, then we don't do anything. Which means that this self.find is like not correctly ever checking if the thing exists. So what's going on here? Yeah, okay, so okay, so what happens here? We say, let me navigate through this tree. Okay. I will say, here is my last valid node ID. We go in here and we say, where's our node? Okay. This is a node at our current navigator spot. So we start the navigator at the root and we say, let's get the root, please. Then we iterate over all of the children of our, not all the children, all the split points, right? So we go 23, 28, 68, 76. While we can iterate these things, let me check if my value, 92, okay, can we reset this actually so that we can, oh, we can't reset it because it's not fucking running right now. But we can run it again just to look. Okay, so here we have 92. 92 comes in here. And so we've looked at the root node. We first look at the root node and we go, let me iterate over all these things. 22, 28, 68, 96. And for all of them, value is greater than. So we keep incrementing this thing until we get to the child. Cool. Now we're looking at this child. So we've like navigated to the correct child, and we go, okay, oh, I see. We immediately, if we say, if it's a leaf, get the fuck out of here. Break the fuck out. Which I guess we can't do here because we need to check down here if our element is in there. So we can't just unconditionally say, we're a leaf node, we found it. We actually need to do it here to give ourselves a chance to do this comparison, which seems reasonable to me. And last valid node ID doesn't get modified until the next iteration, so that should do it. I think. Should do it. Where we go. Yeah, so now what happens is we step and we don't even see that 92 because he immediately goes, nope, nothing to do. Okay, so now we get a 24. And I don't actually know what's happening anymore, which is a little annoying. It would be nice for us to visualize this thing still, maybe? It might be nice for us to like return an inserter who like just is already finished or something. Yeah. So we could say, yo, this thing is our value Our target is the find res node. The B tree is us, hell yeah, and the state is just already finished. And then that should make it so that at the very least we see the thing happen. Here, so we go 92, he's targeting here, and then we just discard him because he already is there. Hell yeah, okay, 24. And it looks like maybe we've just hit the end of our thing, because I think we only have 20 elements in our insert sequence. So can we just up this to like 40 elements and then call it a day? What's he pissed about? Evaluation exceeded 1,000 backwards branches. I see. So it looks like we can't build out this thing at comp time that easily. But also just kind of fuck it, you know? I guess we just won't do it at comp time. And that's totally fine. So here we just return red, boom, boom. We do create insert sequence, and we just don't do it at comp time. Because it's a pain in my ass. Why? Oh, because this is still comp time? Oops. It would have been cool, but it is what it is. All right. So now the 27 comes in here. He goes, oops, already there. 79 comes in. And now we hit another broken case. So what should have happened was our... Yeah, I think what happened here... I think what happened is he thought... Yeah, there's... So here he goes, let me put the 79 in here. So it becomes 79, 81, 86, 91, 92. We need to split this element up because it's too big. It's just too big. It doesn't fit anymore, right? And so the 86 becomes like the center element, and the 86 pops out here, and we go, okay, so we'll split this into two nodes and put 86 in the parent, right? So that's probably what happens here, is we pull up the 86 here, and we see the 79, 81 here, and the 91, 92 here. So the problem here is he didn't realize that he can't advance to the right anymore. So yeah, from his perspective, he's just made a new sibling. And it just happens that there aren't enough siblings that fit, and so that sibling is like rolled over into a child of the first element here, which is a bug. So what do we have to do there instead? What's like the correct answer? 1, 2, 3, 4. Okay, so the correct answer is we probably insert the 79 here, pop out the 92, probably, and try to put the 92 in the parent, 92 doesn't fit. And presumably, we like split the root into 2 nodes or something. Yeah. So, yeah, it must be something like that. It must be something like that. Because I think I read when we were reading like the B tree summary here somewhere. I think somewhere it said the depth only increases when you split the root node. I remember reading that somewhere. Which means that the idea must be that we propagate up. We could read the right answer here. I actually there is this, but we don't like reading right here. It's cheating. It's cheating. Would it be helpful to show the flat array in the top? Maybe. I kind of thought that it wouldn't be. But maybe? How would we show that? Maybe like here you iterate over all of the elements in the data, and then you I don't know. I think it would be hard to correlate. Yeah, so I assume you have to kick an element out here. That's the only option. The 79 comes in, something's got to go out. And before, when things went out, they split the node in half. But we're not doing that anymore. So instead, we just don't split the node in half. We still put the element in, and we fire up a level. So that seems reasonable. Then what? So can we like draw it? This becomes like so we take the 79, we take out the probably the 92 would be my guess here to what comes out. The 79 goes in down here, kind of like this. This becomes kind of like this, right? The 92's up here, and he's like, I would like to go in here now. So the question becomes, how does this shit get split? How does this get split? It must be that, like, you must end up with, I guess, 68 at the top, right? Because if you bring the 92 in here, the 68's now the thing in the middle that would split us. So it must be 68 comes up here in the root. Then you get like, you get 2 nodes, 23, 28, and 76, 92. It must be something like this, right? And so then I presume that to keep the tree balanced, you must have to split these nodes up somehow, right? So it's pretty clear that these guys end up here. Which means that these guys must end up here, right? That must be the way. And is that still like a valid B tree? You go 2, 6, 13, 19, 23, 24, 26, 27, 28, 34, 35, 68, 72, 75, 76, 90. Okay, so I was wrong about which one we kick out here. We kick out the smallest one. We kick out the smallest thing. The 92 ends up like this. Then this is still valid order. Okay. Sure. So what actually ended up happening here? The fuck? So I guess it's that there's some amount of these guys that end up on the right side and the left side of the split. Right? 72, 75 already existed. So 72, 75 just gets kicked over. And I wonder if it's always the smallest thing that gets kicked out in the initial swap here, right? This 79 comes down here. We kick out the 79 back out because it's the smallest. But what would happen if we were inserting a 1 here? Right? Let's like try that case. So let's pretend this is a 1. 1. Okay. So the 1, he comes down here, right? He goes, I would like to go into this guy, please. This thing's full. So we need to kick someone out. I wonder if it matters who. It could be the 19 here. Well, okay, let's work with the let's pretend if we had to kick out the 1. If we had to do that, because we said we kick out the smallest. That would mean the 1 comes in here. 28 gets pulled out. 1 goes down here. And now that can't happen because this guy has to be left of 1 here. So that's not good. So it means that in this case, we probably want to kick out the highest number. Right? We want to kick out the highest number here. Then 19 comes into this guy. The 28 gets kicked out. 19's in. 23 slides over. Boom, boom, boom. Okay. Then this becomes 1923. This gets the first half of this. 68, 76 comes here. Gets the second half of this. 28 comes here. Okay, so it looks kind of like the element that gets kicked out is probably like, it probably depends on if you're on like the left or right side of the parent, right? So probably like on these two, you would kick out the biggest element, and on these two, you would kick out the lowest element, and here you probably still want to kick out one of the smallest or the smallest or the biggest, and you just probably pick one. That's my guess. Okay, let's actually see what happens in this insertion thing. Otherwise the node is full. Evenly split it into 2. Blah, blah, blah. If splitting goes all the way up to the root, so how does like propagation happens? A single median is chosen among the leaf's elements. And the new element that is being inserted. Values less than the median are put into the new left node. Values greater than the median are put into the new right node. So that's what we were doing, with the median acting as a separation value. The separation value is inserted into the node's parent, which may cause it to split, and so on. Oh, so they're claiming you just always pick the middle one. They're claiming you just pick the fucking middle one. So what happens if we do that? We also, like, we can't make a sibling. That's what I'm confused about. They're saying, like, you split this fucker and you take the median value and stick them up, but, like, how can you split this if you have nowhere for the split to go? You know what I mean? I guess this becomes, like, yeah, I don't understand. They, like, I guess what they're saying here is, like, you add a third element here that just doesn't work. They, like, temporarily let this guy have 1 extra child, which seems kind of like bullshit to me. Seems like bullshit. But the idea of that still seems reasonable. Like, splitting at the median probably results in overall more sane behavior. Probably. Okay, so can we run that simulation? 79 comes in, he goes down here. We go, okay, too much stuff. 86 come out, please. And then we have 2 new things here and here. 79, 81, and 91, 92. But, like, Now what? What happens in their picture? In their picture, they put the 7 in here. He splits. Oh. So in their world, you can assign you would probably like return these two nodes up with who you're like these two nodes are going to be parented to this guy inserted with this, right? Like root inserted with this. And then probably what happens is like 86 gets put here. Then you get like the 68 gets popped out because it's in the middle. I don't really understand how like these children work though. Right? Like 76, 86 cannot parent this. It's impossible. Because they need the 72, 75 here to balance out the 76. So it's like as you walk up the parent, you're like reparenting your direct children as well, probably. You're like, I'll make a new node and I'll move these 3 things over there or something. Yeah, I don't know. I'm quite confused. Quite confused. I wonder if it would be like probably the fact that we're storing everything in like precise locations instead of just heap allocating and like child parenting nodes and stuff might be making this more complex. It might be. I also wonder if we have to kick out the median. I would bet that my idea of just not doing that is totally fine. So let's run with my idea of just kicking out the top or bottom element depending on which side you're on, and see if that kind of plays out nicer. Because I like my gut says it does, and my gut also says that if you can construct a valid B tree out of that, then it's not any different than like just a different insertion order. I could be wrong there, but that's what my gut says. So fuck it. Fuck it. We'll just run with what the gut says. So we need to, when we split a node, we need to check if we are out of bounds. So we need to be like, if the node child index for num children and like self is target, the right word? Yeah, target. So we're like, node child index. This is like what we are. If this is equal to num children minus 1, because off like length is 1 more than index, then for now, can we just return error for now, just to make sure that this is where the change needs to be made. Okay, so we come here, we refresh, everyone's happy, then we throw some guys in here, and we don't which is, we do, we see here. But weirdly, it feels like too late. Wait, yeah, this doesn't seem like a problem at all. Are we? Oh, we're running the server twice, which of course will cause issues. Okay, here we go. So we're uh-ohing directly when we're trying to split this node. That makes sense. Well, it makes sense. And actually, I've changed my mind here. It's not if we're that this just happened to work because we're on the rightmost edge. We actually need to check if we need to check if like our parent. We check our parent and we say if parent node num elms is equal to node capacity. That kind of feels more reasonable. Yeah. So let's see if that still falls the fuck over. Yeah, okay. That's still broken, which is great. So now we've kind of found our condition where we need to propagate. So here, instead of actually splitting the node, we just don't. So we just check. I think we still want our index. So here we say like node child index is node, what was it? Child index like this, right? So if node child index is greater than num children over 2, we replace the highest node. Yes. Otherwise, we replace. Yeah, that seems reasonable. Where does split node come in? Split node happens if we. This feels more like an insertion thing than a split thing. So I kind of want to do this somewhere else, to be honest. Yeah, because split node happens when we try to append the value, it doesn't work, and so we split. Append is kind of where we have the sorted elements. So I'd be kind of curious to know what happens if we put this in the append section. So what happens here? We go get by node. Okay, append this value. Oh no, this guy, yeah, append, he just sorts. So it must be in split where he does the with extra shit. Node splitter is where that's put on. I remember now. Okay, so we have our node splitter. Okay, yeah, sure. So I guess we just replace. We replace some child depending on if we are greater than children of 2. So if they were greater, we remove the lowest, and if we're at the lower end, we remove the highest. That's what we said, right? So we remove 0, else I guess it's just node capacity -1 or something. Yeah, well, it's gotta be. So then we just say like node elms replace index. I'm assuming here that in order for this thing to be split, it has to be full. So let's just kind of double check that here with a little assertion. And we just say like new val is this thing. And then we replace it. So we say node elms replace index is equal to val. And then we say, all right, let's just try to put this guy in the parent. Yeah, seems kind of reasonable. And then I guess we actually don't need like the sorted data here because it's already sorted. Oh, we do, because we need to know how it's sorted with our extra data. So here we have our node splitter has that information. Node splitter has like, he has the sorted values that were in the node plus the value we're trying to insert. That's what this with extra field is. And I guess it's literally just node capacity then. And then, because with extra has one more, and then it's so our new val is now we need to know if we're actually replacing though. We need to know if we're actually replacing. So I guess we could say like if new val is less than node elms 0, we don't replace anything. Else if or self val is greater than node elms node capacity -1. Yeah. In either of these cases, we just return val is self val and target equals parent ID. We just take the value and we try to put in the parent. Otherwise, we replace it. Yeah, otherwise we replace it and resort. Okay. That seems kind of reasonable. Why is he pissed about this? Value with comp time only type comp time int depends on runtime control flow. Do I really have to do like as use size here? Oh, it's actually probably more that this has to be like as use size here, maybe. So that he doesn't get confused. Yeah, he's like, those are comp time ints. What the fuck, dude? Okay. I think something got broken there, so here the 79 comes in here and he crashes. Okay, so what's happening there? It's that the number of elements is not equal the node capacity, which is kind of surprising there. I would think it would. We have 4 elements here, node capacity 4. So what the fuck? Why is that not like that? 2. Hello? 4. The fuck? uh the actual fuck. No, seriously, what the fuck? Did I call set data on this guy too early? I did. So this guy has to come down here. We don't set data until later, baby. And probably we just don't use this node splitter at all till down here. Okay, let's try it again. Boom, 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 boom. Okay, so here's the overflow case. This okay, so that's good. So we saw that the 79 was less than the 81, and then we're immediately just like, fuck it, we'll try to insert the 79 into the root. So that's an improvement. An improvement for sure. Now what's going to happen is he's going to try to insert into here, and I don't know what... Right. So in the case where he has to split the root, he assumes that he can put into the children here, 0 and 1. But that's because just in the first case that we did, the children were empty. So we need to say, like, if we probably need to do like something that's like, let's go back. We go back. Okay. So we put the 79 here. And I assume that we have to pop the 68 out, which I think we're already doing, right? I think that when we hit step here, the 68 does come out, so that's good. Oopsies. And so the 68 pops out, 79. Then we need to put the 23 and 28 and 79. These do go actually in these two nodes. That's correct as well, which is kind of interesting. What we have to do is we have to, before we do that, move all of these guys forwards. So we have some like node storage that's like, Valigo, thanks for the raid. What's up? What's up? What's up? What's up? We are working on B trees for those of you just coming in. We are trying, B tree basically says, for each node in my tree, I have children on the left are smaller than children on the right. So I go 2, 6, 13, 19, all less than 23. 24, 26, 27, all less than 28. 34, 35, all less than 68. The idea here is that like you have like a tree of sorted elements that it's like pretty fast to iterate through due to like better memory coherency, I guess. So we're just trying to fix our propagation of max insertion things. So right, like the 79 is going to come in here. He doesn't fit in here, so you have to like propagate something up to the top. And we're just working on that. I hope you guys had fun on Valigo's stream. Thank you for the raid. And we're just going to keep going. We're going to keep going. Okay. So we say here, 79, less than 81. Boom, come up here. And I think all that has to happen here is we pop out the 68, which is happening. And we just have to find, I guess it becomes these two nodes. Maybe these three nodes. These three nodes are all going to be less than 76. These four nodes are all less than 76. Ah, fuck. Wait, is that a problem then? Is that a problem? We cut and paste this earlier. I thought. We need to draw out what we think the final result is to make sure that we think this is valid. I thought it was, but now I'm questioning myself. So this 79 comes in here, which pushes, oh, it becomes 23, 28. Oopsies. This 79 becomes a new layer. 23, 28 comes here. Then we get everything that is less than 23, 28 as a child here, plus this guy. Yes, that's what we said. Then the 68, 76 comes down here. All of these guys. No, wait. I think that this is a problem. Actually. Because one of the constraints of the B trees is supposed to be that you don't end up with empty nodes. But in this world, you actually have an empty node here. Fuck. You have an empty node here. Because there's two nodes in here, which means there's 3 children. Which is no good. No good. Which means that my idea sucks. It means that my idea of just kicking out the smallest one doesn't work anymore. Fuck! Okay. I mean, that's good to know. So let's think again about what the right answer to this is then. The right answer, according to that Wikipedia, was that 79 comes down here. The 86 gets popped out because it's in the center. So then you end up with like this like extra thing here. 91, 92, like this. You end up with these like 6 nodes. Then I guess like these 3 nodes have to end up on the right side. These 3 nodes have to end up on the left. And then this comes here, I guess. 68, 76 sits here. No, that's not right. Oh, but this 86 comes here, right? That's why. So the 86 comes to this. The 68 gets popped out because it's in the center. Boom. Oopsies. Boom. 78, 86 goes here. That works. 23, 28 goes here. That also works. 68 goes up top. Okay. Sure. So now the question is just how the fuck do we get into this state? How the fuck do we get here? Because up until this point, we've been assuming that we can just write into the valid memory. I guess we could just say that, like, in this case where we have to split and we run out of room, we know how the split is going to propagate. So we must be able to, okay, here's existing state, here's end state. So we kind of know that that we have to write these guys into these child slots. Yeah, we kind of know where these are going to end up. We know where they're going to end up. They're going to end up one layer down. I guess we don't really. So if it's this guy, they end up. Oh yeah, wait, there's a lookup here. It's that we can draw a map here, I bet. We can draw the map. So it's after split, say we were splitting this guy instead, just hand wavy. It's 1, 2, 3 end up here, 4, 5, 6 end up here. Simple, right? So I guess that we just have to figure out what our split output is. Right, so here we know that we're at index, like, we know we're at index 0, 1, 2, 3, 4, and so we know that we're going to end up at 0, 1, 2, 3, 4, and 5 in this layout. Okay, and if we were splitting this, we know that we're index 0, and so we're going to end up at indexes 0 and 1 over here. So that makes sense? That makes sense. We can just directly write into where we're going to end up on the output. Now the question is how do we make sure that we don't get overwritten later? So then we go up a layer, right? We go up a layer and we say, okay, we're going to split our parent. We know already that our parent's going to overflow. Because that's how we decided that we need to go down a layer. So if we know that our parent's going to overflow, we could move all this shit like literally right now. Yeah. Yeah, we do that. We just move all of the shit over like literally now. Haha. So yeah. So here we just go move all siblings one depth layer down. And then presumably that propagates okay. Presumably. Because then we would go up a layer, and let's just say theoretically this wasn't the root. If we go up the layer and then we have the same problem where we're trying to insert one extra guy, we just do the same thing, and now we copy all of those guys one layer down, and they fill the slots that we just emptied. Seems kind of reasonable. Seems kind of reasonable. So, yes. Okay. So we just have to create these like mappings of where we're going to end up. Oh, God. So... for everyone up until us, right, we have to do a copy one layer down. Then we execute the split. So we have our node splitter here. And we say like, okay, let's just pretend that we have a like next layer node function that takes in where we are, presumably. I guess it only has to take in this. Yeah. So we'll call this like target node ID. Like this. Next layer node, I think, is actually kind of straightforward. I think that he needs to do some sort of like, he needs to know the number of children that each element has. And he needs to know my node ID. And he's going to return a node ID. Okay. And all he has to do is like, remember that this stuff is stored as like a linear array of shit, right? So like the root is at 0, then root's children's are 1. We'll pretend that there's 2. 1, 2. Child 1 gets 3, 4. Child 2 gets 5, 6. And then here, child 3 gets 7, 8, right? And so on, right? So we kind of store like first layer, second layer, third layer, fourth layer, like sequentially. And so what we do is we have this like depth start iterator that says like, he basically returns like this, then this, then this, then this. And all we have to do is find where the next layer starts, which we actually have like node depth bounds here. So we take in our ID and our num children, and we get like bounds here. And our thing ends at bounds 1, okay? And so all we have to do is we take our ID, percent num children. I think that's right. Can we call this index? I think that's easier. We take our index and we say the start value, like parent child start, parent first sibling, I guess. So if we're less than 3, we're gonna be at the beginning of the next section of depth, right? We're gonna go like if we're in here 3, 4, 5, 6, 3 and 4 become children 7 and 8. So it's kind of like this: 3, 4 go to 7, 8, 5, 6 go to. Then there's like 9, 10, which are going to be empty, and then 5 and 6 go to 11, 12. Yes. Yes, 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 yes. Something like that. Wait, hold on. Hold on. Something along those lines. We're close. We're close. It's not quite what I said, but it's very close. So can we actually just log these in terms of like their node IDs right now? This is literally 0, 1, 2. Then 3, 4, and 5 are missing, which makes this 6, 7, 8. 9 is missing. 10, 11, 12. 9 and 10 are missing, so it's probably like 11, 12, 13 or something. Something like that. 0, 1, 2, 3, 4, 5 are missing. 6, 7, 8, 9, 10 are missing. 11, 12, 13. Yeah. Okay, cool. So I think 6 should be the start here. And 11 is 6 plus 5. So we say if index is less than or equal to num children over 2, I think. 0, 1, 2, 3, 4. 0, 1, 2, 3, 4, 5. Num children is 5. So if we're less than or equal to 2, which is 5 over 2, integer truncation, that becomes 4 over 2, which becomes 2, which makes this correct. So if this is true, then we're at bounds 1. Else, we're at bounds 1 plus num children. Yes, that's gotta be it. That's gotta be it. So then we just literally go like first sibling plus we'll call this like split point, I guess. And we say first sibling plus my index minus split point. I think that's like we're getting really out there. But I think it's something like that. This is quite out there, but we could try it, okay? So let's write some tests here. Okay, so first let's just make sure that if we, try error, our test will fail. He's mad at 395. Oh, sure. So we're not really done here yet. Okay, so we do see error. Hell yeah. So now let's just check. So next layer node, given 4 children, 5 children, and we are node ID 1. Node ID here doesn't work. Because we have an index that's greater than the number of children that fit here. So this has to be child index. It has to be. Which means that, like, I guess we kind of do next depth start here. Or like sibling target node? Sure. So this is the node that we're splitting, I guess? Yes. Okay. Okay. So we say that we're splitting something in the layer of node 2 with child index 0. So that is this guy right here, the first child of the root. We are expecting this guy to give us the first child of the next layer down. So that's 0, 1, 2, 3, 4, 5, 6. We're expecting this guy to move into 6. Okay. And this should be a node ID. Yes. Okay, so does that pass? No, because it doesn't even fucking compile 182. He's pissed off because node ID. Oh, sure. Sure. Hey, what's up? Yo. We're working on B trees. We're slow. And that's okay. That is okay. We'll get there. Okay. So this didn't work. He expected. He's not even telling me what we got instead? Little bitch. Is it because he doesn't know how to print it? Do you have to, if I write, I expect to get node 6 here, and I write dot value here, does he behave a little better? Expected 6, found 4. Okay. So that's good. So what is happening here? What is happening here? That means that the bounds here. Okay, if we put in like node 3 here, what do we get? Found 12. What the fuck? 1. Found 5. So it's got 4, 5, 6, then 10, 11, 12 or something. So the 4 here is just totally wrong. Where's the 4 coming from? The 4 is coming from bounds value here. Bounds value here must be 4. Which means that node depth bounds is returning 4 for some reason. Let's look at this. So we have root at 0, his children 1, 2, 3, 4, 5. So like the 4 is like, what the fuck are we talking about? What the fuck are we talking about? Where the fuck is this 4 coming from? The fuck? Is this fucking broken? Node depth bounds, if we use... Oh, did we get the ordering wrong here or something? No, okay, so we have, node number 2 with 5 children, with num children 5. I'm expecting that, like, the start of this layer starts at 1, and the end of the start of the next layer is 0, 1, 2, 3, 4, 5, 6. That's what I expect to see here. Dot value on both of these, I think. Okay, so that's fine. Confusing, which means that like this thing not behaving the way I expected is something else. Something else, right? Because the bounds that are returned by this call should be 1 to 6, which is correct for the next layer. Okay, so that's good. So then where the fuck is the 4 coming from? IDX minus split point. Ah. Because this IDX minus split point should only happen if IDX is greater than split point. Yes. So I think it's like this. Boom. Okay, cool. That's better. Okay, so here now we say, okay, we expect that we say we have 5 children. We're looking at our something the first sibling in the node layer 2. I'm expecting that anything here all gives the same answer. No matter which node we pick as our sibling, that should all be the same. Okay. Now we say, let's give me something at like 3. At index 3, 2. Yeah, so index 2, we should end up at 6, 7, 8. That's what we said. And then as soon as you jump to 3 now, he's like, wait a second. I'm not a sibling here anymore because we're going into like, where the fuck was our layout thing? We lost it. But it was like once you pass the halfway point, you jump to the next node. So this should be 8 plus num children. This should be 13. Fuck. Found 16. Yeah, I'm a dumbass. 14. Was I off by 1 on the count here? So we have to draw it out. We have to draw it. So we have root 0, 5 children, 3, 4, 5. Then each of these has 5 children. So 6, 7, 8, 9, 10. And then 11, 12, 13, 14, 15. Is that right? So if we're trying to split here, we should be filling 6, 7, 8, 11, 12, 13. So I was double wrong. And we found 14. So we're off by 3. What the fuck? 6 plus num children. Oh, yeah, wait, this was right before. I'm fucking high. Ah, found it. Expected 11, found 12. So that's a sane off by 1 here. We'll just tuck that in there. Okay. So is that right? Let's just double check one more time. 1, 2, 3, 4, 5. 1, 2, 3 go into 6, 7, 8, 9, 10, 11, 12, 13. And then 4, 5 plus the 5.5 we'll call him, go into 11, 12, 13, right? So we should also check here that 6 goes into 13. Dude. Oh, it's because it's 3, 4, 5. I'm a dumbass. I'm a dumbass. Boom. All right, baby. Okay, we've got something. We've got something. So now when we're doing our split, we can say, let's go through each of these guys. Let's get the next layer node for this guy. But now we know this guy has more parameters. It's got num children, and it's got like self-target as the node that is like a sibling of who we're splitting, and our IDX. Okay, cool. That's pretty big for us. So we get our child index. We get where we're going, where we're copying to. And I guess we just say target node is going to be target node is B tree get by node ID and resize because it might be out of range. The target node ID. We just say target node is equal to whichever node we're coming from. So we have the parent node here. We have the parent ID. So we should be able to go like from parent ID at child index I. Target node from and target node 2, and target node 2 is just equal to target node from. Okay, so that's a copy one layer down. Sure. Which sounds like this gets pulled out into a function, right? Copy, copy down, which is a child index. Surely. Sibling node. I guess we'll just take itself here. Dude, this is getting crazy. Copy down parent IDI. Okay. So let's just start there. Let's just start there. So no member function name copied down because this is supposed to be inserter. And this guy, I guess, const inserter is fair fair to me. I guess fuck it and cast here. Error unit is ignored. Try. Target node 2 cannot assign from constant. Oh, here, if I just do a little dot star here. Oh, this is an ID, which means that, like, we need to be a little careful here. This is to ID, from ID, and then we do a double like this. That's gotta be it. Okay, so let's now see what happens when we start fucking shit up. So here, I'm hoping to see, I guess, like, these 4 guys here all end up one layer over here. But instead he crashes, which is interesting. Hello. Glad to see someone grinding Zig. Hello, hello. What's up, what's up? So that means that the node here is invalid, which is kind of interesting. Like, we were segfaulting on node dereference. Because this resizes the array, which means that this node is invalid now because he's a pointer to something. Also, so is this parent node. So that means kind of like these guys have to come in here. Oh, this is also weird. Node splitter init node. Okay, is this how does this feel? Node splitter init node takes in a const node. Does he stash this guy? No, he just mem copies out. So this is totally okay. But this stuff is not okay, so we move it in here and reassign here after the resize of the array. I guess there's like a pretty big chance here this like invalidates node pointer. Right, so that's kind of fucking bad. Yeah, there's just lots of problems here. I guess what we should do, I guess we could do it the other way, where we say, oh, this is ugly. Oh, this is awful. Like, we could just reassign the nodes here. Or we could just call get by node ID fucking everywhere. Like, we could do that. which is kind of shit. Everything's shit. I don't know, man. For now, we'll just do this. I don't know, man. And then everyone else down here should be fine, and then I'll just leave a fix me down here. Oh, which we already have. Hell yeah. Okay. Okay, so step or refresh. Okay. Boom. Okay, that's really good. So we see the first three elements end up as the first child of this guy. And then I think that what's happening now is that the parent has not been like updated, so I don't know if these guys know how to display themselves. This might be a visualizer problem. So if we look at the data here, we do see a 34, 35, 72, 75 in here. Oh, 34, 35 is here, but 72, 75 is in here as well, but missing from the visualization. Okay, can we go back here? So where, fuck. It's here. So here we're expecting to see 72, 75, 81, 86, or 79, 81, I guess. 91, 92. But we don't handle the second half yet, which makes sense. So yeah, right, okay. That means that this is working. This is working. Right, we see this 2, 6, 13, 19 was copied down here. That's huge for us. Absolutely fucking mega big, huge. So that means that we have to do then like can we do like a what the fuck is this? Split child index, I guess. Then we go, I guess we could do like var child index is equal to 0 while child index is less than split child index. Defer child index plus equals 1. That means that this can now be a child index like this. We can get rid of this int cast and we can just use child index here. Okay, so now child index is the node that is being split, right? So we take the node splitter and we take the left elements and we put these in the node to the right. Yes. So this is like I don't know. Get node by ID and resize given we need to somehow get how did copy down get there? We need like our target here. Node child this stuff. Yeah, okay. Target node ID target node something like this. This is all like very prototype code. You can tell we haven't really figured out what this is supposed to look like yet. But eventually we will. Eventually we will. So we have like some node now, and we can be like target node and set the data of this node to the left half of the split of we're doing with this node. So this node's getting split into two pieces. The left half goes into one node, and we do it again with the right elements. Yes. And then we just have to do the rest. So while child index is less than or equal to node, like num children maybe, right? Because there's 5 children. We're trying to copy 6 chunks of data down. We copy down from the parent ID to child index -1. That feels fucking correct to me, and then all of this stuff just kind of dies. Maybe. But we probably have to return the new target. So we are now saying that we want to take the thing from our node splitter, the element that we want to set to the parent. We say, go do your thing, baby. That seems kind of right to me. So boom, 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 boom. Here's the part where it breaks. And we're hoping to see 81, 86. Okay, we're hoping to see 86 come out. The 79 comes down, 86 comes out. And we're hoping to see 79, 81, 91, 92. Yeah, okay, we can draw what we're hoping to see here, and then we'll check if we actually get it. We are hoping to see 79 comes down here. Now 86 is in the center, he comes out. 91, 92 get split like this. These guys should go over here. These guys should go over here. And we should have like maybe like, you know, some arbitrary nodes in between. Oopsies. Right? Some shit like we don't really give a fuck, kind of whatever's over here. But we're hoping to see this column here. Which we did not. We fucked this up. So we do see a 91, 92. And we do see 24, 25, 26, 34, 35. But we do not see this stuff, which is what we were hoping to see. Now, can we look at the data? It could be a visualization bug. So it looks like not, though. It looks like 72, 75 really is the last thing here. And it looks like that we've totally lost, like I don't see, oh, 79, 81 is in here at node 5. Oh, sure, but that's where it was before? 79, 81, 91, 92. Oh, wait. We see this. 72, 75, 72, 75. 91, 90, 79, 81, 79, 81, 91, 92, 91, 92. So it looks like we just copied them to the wrong spots. That's how it looks to me. Which is kind of surprising to me. Kind of surprising. So can we, okay. So the 2, 3, 2, 6, 13, 19 is lost from the copied down data. It's supposed to be at 1, 2, 3, 4, 5. I believe. So it looks like probably this stuff could be wrong. Okay, let's comment out things and kind of bring them in one by one and see how they're fucking shit up, and that will give us a better clue probably. Refresh. Step. Okay, boom. So this is fine. Now, all of the stuff that we expect to see here is here. Now, we add back literally just one thing, one little thing, which is boom, 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 boom. Here's the breakpoint, boom. So here we were hoping to see this data go somewhere. So the data to the left of the split. Data to the left of the split. So that's supposed to be the 7981. We were hoping to see that somewhere in here, and we're not. So the question is do we see it somewhere in there if we look at the data returned by this guy? Okay. Data, we're looking for, what are we looking for? 7981. I guess we're also supposed to see 7275 somewhere. We do see 7275, and we do see 7981. 7981 has very clearly gone to the wrong spot. Okay. I genuinely want to know why you would need to do this by hand instead of asking ChatGPT. Dude, I fucking tried. I fucking tried yesterday. I hear this shit all the fucking time about people saying how good these coding tools are. Every fucking time I try them, they're fucking dumb as bricks. I can't believe you guys use these things, dude. I used DeepSeek yesterday, and I was like, write me a B tree in Zig. And he did something, and I was like, I would kind of want like these constraints handled. And then he just like starts like fucking referencing fields and structs that don't exist. He doesn't even know what fields in the structs he wrote are in like a 200 line file. How the fuck is anybody using that shit? Like I don't understand. I don't understand how every fucking time I try to use these tools at all, past the very, very most basic implementations of something, it just like shits itself. It's crazy. I'm cannot believe I like either I'm like old, out of touch, and can't fucking use this shit, or like everyone's fucking lying to me. And I keep leaning to every time I like poke and prod and test this stuff, it's like it's so much worse than everything I'm seeing online. I think they're good at making edits, not genuine code though. But the problems I see are I'm like, okay, I asked to write me a circular buffer. Simple, right? I was like, DeepSeek, write me a circular buffer. And he did something, right? And I'm like, okay, there's this trick you can use where you can say, instead of like in your circular buffer, storing like circular buff, right? You can do like you can say you have a head pointer and a tail pointer, right? But you have this problem where if your capacity is like 10 and you have like head minus you're inserting into some buffer, right? You have like buff 10 elements, right? You write at head, chill, that's fine. But if you want to know if the thing's full, you're missing a bit of information here, because if you say like buff head equals thing, buff or head plus equals 1, and then you say like size is head minus tail, right? Hand wavy, right? And then when you read from the thing, you say like buff tail, and then you do tail plus equals 1, right? Then you have to make sure that when you increment this thing, you modulo the size of the thing so you wrap around the end of the buffer, right? Chill. Now, you can't tell the difference between fully empty and fully full, or fully empty and full. You can't tell the difference between empty and full with just head and tail here. So the LLM was like, okay, I know that you can't do that. So I'm going to be like, let's throw a count side in here. And I'm like, yo, okay, there's this trick you can use. LLM, there's a trick you can use. And it's that if you allow head to become 2 times the length, right? Then all of a sudden, you can store both capacity and count. Like you can store everything you need at once, and all you have to do is modulo size the head. And he just like shits himself. He just shits himself. He doesn't know what the fuck to do. And he's like, yeah, that's a valid trick. And then he just like spits out something that doesn't fucking compile. And it's like, or is wrong. And then I'm like, this is wrong for this reason. It's like still wrong. It's like, dude, a circular buffer is like one of the most fucking simple things you can do. So like, either you have to like just go deep out of your way to like poke and prod this guy into doing the wrong thing 10 times in a row to get it to do it right, or you have to like be very careful about how you instruct this guy, which I don't think that like being like, I want to make a circular buffer, I don't think that's fucking a hard thing to do. I don't think I shouldn't have to like fucking craft this like super complex query to be like, write me a fucking circular buffer, right? So like, what the fuck is it doing? I just don't understand how people are using this shit in a way that doesn't like fucking shoot, like make it shit himself. I don't understand. I don't. What about web dev? It can do anything a full stack can do. It's just like anything that is like simple enough that it can do. It's not hard to type it out yourself, and anything that is complex and worth thinking about, it can't fucking do. So like, that's why I don't fucking use it. It's shit. It's shit. Every time I use it, it's shit. And I can imagine if you are like a baby bird and you're just like, I want program, and like the fucking chat GPT mama pukes some garbage in your mouth, and you're like, okay, I'll take your garbage. Great, this is great, I love garbage. And it's like, I swear to God, I'm not crazy, and I just cannot fucking find. I think that it's just wrong and people don't notice. That's the only thing that I can think. So, I don't know. That's my rant for the day. Subsparrow, garbage in, garbage out. Anyways, let's try to figure out why my garbage doesn't work. Because when I'm wrong, I'm not mad. Okay, 79 comes in here. It must be that like the target for the second half is wrong. So what was supposed to happen is he was supposed to write down here somewhere. Oh, I wonder if just like if the render. No, we checked the data. The data is wrong as well. Okay, so it must be that this is wrong. This has to be wrong. So num children, parent ID, child index. Can we like just log this thing? Can we just breakpoint here and just see what the fuck is going on? Boom. Okay. Boom, 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 boom. Slam step. Get to the part where he's trying to break these things out. So we have node splitter. We've got 79, 81. We're trying to set those in some node. We got fucking target node 85, which is super wrong. Super wrong. We are trying to set this into target node. Where is our like picture of numbers? Root is 0. 1, 2, 3, 4, 5 are his children. 6, 7, 8 is where the first thing goes. 9, 10 are empty. And then 11, 12, 13. This is where we're trying to go. We're trying to write into... I guess we should log maybe where each of these guys goes first as well and copy down. Can we just write like std debug print target node to ID. This is the interesting thing here. So what we're hoping to see here is 6, 7, 8, 11. That's what we're hoping to see here. And we're probably not seeing that, but that's the correct answer. And if it's wrong, then we can start debugging. Boom, 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 boom. Okay. 6, 7, 8, 11. Wait, that's actually kind of right. Wait, hold on. That's kind of sick. Interesting. That's interesting. 6, 7, 8, 11. So now I'm like confused in more ways than one. Maybe our visualizer is also broken. Oh yeah, so 11 has 72, 75. So that's actually kind of right. That's kind of right. And it's probably that the tree doesn't have an 11 anywhere in the tree right now. It does here. Node 1, 2, children 0. I wonder if it's just that the canvas for this thing isn't big enough. Can we just like height like 2000 or something? Like let's just fucking... Oh, wait. Okay, wait. So we just weren't showing everything. Okay, wait, that's huge for us. Absolutely mega big. Okay. So now let's add one more. The step button is like way the fuck down there, which is a little annoying. Okay, so here's the problem. Because we did definitely see target node ID of 5 somewhere. Right? We saw std debug print target node ID. Target node ID value. And can we put the same thing here for a second? Okay. Target node ID, yeah, 6, 7, 8, 11, 5, 6. So we're doing something brain dead fucking stupid there, I guess. I just don't know what it is. So can we just print the inputs to this thing and then write a test for it? I guess that's kind of the play. Okay. P num children. Oh, that's 5. We know that. Parent ID 0. Whoa, 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 whoa. Wait, is that right? Yeah, that's right. Child index 4. Dude, this is like the simplest fucking case. Oh, I'm a dumbass. This is supposed to be the sibling ID. I'm a fucking dumb, stupid dumbass. That's why. It's not the parent, it's supposed to be sibling. There we go. Boom. Step. Now he crashes. That's improvement. Index out of pattern. 30, length 12. Okay, so that's 589. Get by, oh yeah, because we need to get by node ID and resize. We have to resize the array because we're fucking adding stuff that wasn't there before. God, it's so simple. Set data can fail, I guess. That's kind of surprising. Why can this fail? Oh no, this can fail. I see, because resizing can fail. Of course. Of course. Wait, okay. Moment of truth. We gotta fucking move this step button up a little bit. But okay, that's like a little better. But definitely not quite right still. So we got 6, 7, 8, 11, 30, 31. Wait, 30 and 31 are still wrong. We wanted 12 and 13. Dude, I feel like I'm going to lose my mind. Copy down. Copy down. Parent ID. Next layer node. Next layer node. Yeah, I'm fucking mental. We're missing a critical piece of this thing. Dude, I feel like how the fuck did we end up here? How the fuck did we end up here? Okay. This is what it should have been the whole time. I don't know how we got it so wrong. We were just using the fucking wrong call. Okay. Boom. There we go. Okay, we fucking got there. So now we see that is this correct? No. No, it is not. So we were supposed to take the 7981 went here. Great. We're missing that the 9192 was supposed to go here. Probably because we used left elms twice here. One of these is supposed to be the right side. Right elements. Boom. Boom. Step. There we go. Okay, we fucking got there. 2, 6, 13, 19, 24, 26, 27, 34, 35, 72, 75, 79, 81, 91, 92. We fucking finally got there. It's so fucking hard for us. Okay, so now we have to clear our parents. Our parents have to go like fully dumb empty because they're going to be propagated down from the root. That's what we said. So here we need to go like node equals self b tree get node by ID. And we go here and we just put a note here that says resizing invalidates previous node pointer. And I guess this is like literally just like an array grab, so we could just it's fine. Fix me. This should be harder to get wrong. And we go like node num elms equals 0. Okay, so now when we get to that point, bop. I guess it's showing it even though that's kind of surprising. What if I do this? Set data to nothing. Oh, it's only this node. We actually have to set all of our siblings to 0. Technically. Yeah, that's true. That's true. So we have to go like for like 0 to num children. We go like to clear ID is like node child with num children, and the node is like parent ID, and like the child index is I, and then we go like to clear is equal to clear ID, and then we set the data, and then probably we should probably do something here that's like fix me only do this in debug mode, or like when visualizing. Like this should not be done in the happy path. It should only be done for like visualization purposes. Okay, so now hopefully there we go. Okay, so we then pushed all of the guys that were in this layer before down a layer, and now they're empty. So that's really good, which means that now when we work with the root, when we split the root, he can just fucking, maybe he can just work. Wait, that just kind of does what it's supposed to do. Let's fucking go, baby! Wait, that's actually kind of correct. That's hype. That's hype. I think that we probably have a bug still, though, after this, where 2 is trying to insert into here because we have to flag these guys as leaf nodes. Or internal or inner nodes. And I guess it's like only do this when in debugging. But this kind of comes up here. So it's kind of like this, I guess. Okay. Can we fucking fix this, like... How come if I put, like, these buttons here up above, they end up below the canvas? I guess we'll just kind of do this. Stick them in some divs. There we go. So now this is always at the top. We throw some stuff in here. We now... Is this a valid B tree? 2, 6, 13, 19, 23, 24, 26, 27, 28, 34, 35. All of those are in order. Then we go on to the next segment of the tree, 72, 75, 76. Oh no, we go up here first, sorry. 68, 34, 35, 68, 72, 75, 76, 79, 81, 86, 91, 92. That's a fucking valid B tree, baby. Then we put this 2 in here. He tries to go in here. This 28, he's like, I already exist. 10 tries to go in here, which should split this thing, which would move these guys down 1. Boom. Which I think is good. Then the 10 gets popped out because it was the center, and he tries to go in here. Boom. Oh, come the fuck on, baby. Come on. 41 tries to go in here. Boom, simple. 46, boom, simple. 35, already there. 80 tries to go down here, which should fit fine. 85 also fits fine. 68 already exists. 6 already exists. 7 goes in here. 36 splits this guy. The 36 will come up here. Because the 36 is in the center of this. So these guys get split in half, basically. And 36 targets here. Boom. Oh, this is working great. This is working wonderfully. 70 goes down here, already there. And then we run out of stuff. I think that's kind of working. Let's just keep going. I would love to keep sampling until we see another layer drop, which I guess probably won't happen for a long time. But we can at least like watch how it reshuffles a little bit. So can we change this insert sequence size to like 1,000? Just like fuck it, we won't run out. I don't give a fuck. And then we were at 40 before, so we'll just continue on from where we were before. Okay, boom. 50 comes in here. 42 splits this. So that will end up with this guy getting too big. And I don't know what'll happen. He started a new layer. Fuck. That's bad. He shouldn't have done that. He shouldn't have done that. Oh, no, we're not done. No. Okay, so the problem here is that he should have, instead of making a new layer, it needs to be like 10, 20, Jesus Christ. So we have the 1023 here. That's all fine. And it's that, like, this stuff should be the child of this guy. Right? 34, 35, 36, 39, 41, 42, 46, 50. Then we have stuff above 68, which is all of this stuff, which is wrong as well. Dude, this problem is like way deeper than I thought it was. Interesting. Interesting. I wonder if it's like somehow this is supposed to be more balanced right now and it's not. Well, I mean, but everything that was 68 or below is ending up in here. So the 68, when it was split, was reasonable. So you need some way to, like, here you must have to propagate up something. What if here we propagate up the 42? The 42 tries to go into here. We propagate up the 28. Then what? Like, somehow we need to, like, use these nodes over here that we're not using. Interesting. All right, well, there's more to think about. So we have now we have fixed we have fixed insertion into 2 layers. So we can split the root node. We can split 1 layer below the root node, and then we fall the fuck over again. So I guess another day of B-tree insertion is the way to go. That's kind of fun. It's crazy. I really did not think this would be this hard, which is kind of like classic programming. Super classic programming. Cool. So I guess we'll just come back. We'll slam our heads into this again tomorrow. Thanks for watching, guys. I hope you like what you saw. If you like what you saw, we stream most days at around 12:30 Pacific time to 4 o'clock Pacific time. It is 3:55 Pacific time now. So if you are online right now, you should expect to see us between 3.5 hours ago and now. But if you are watching on YouTube, it's not that simple. The YouTube link, it's in the Twitch description. It's like right here. It's right. Mute. Shut the fuck up, me. Shut up. Let me mute. Dude, fucking software. It's right here. YouTube. What were you gonna say? What was I saying? Yeah, on the YouTube, things are organized into playlists, so you can keep up with current progress. This stuff should end up in the music section. So I don't know. There's a music playlist somewhere. If you want to follow along, that's where it'll go. There's a GitHub link in the Twitch description too, where code for this will eventually go up. Not right now, but someday, sometime, somewhere. Oh, you don't have the link? I mean, okay, it's just the same name everywhere. So if you just copy paste into YouTube, copy paste into GitHub, it'll be the same. What else? Like, subscribe, Twitch Prime, baby. YouTube, peace out. Twitch, let's find someone to raid.